This is my report all about eigenvalues and eigenvectors. So what are eigenvalues and eigenvectors? Fundamental concepts in linear algebra that have wide applications in various fields, including physics, engineering, computer science, and economics. They provide insights into the structure of linear transformations and matrices, helping us understand how these transformations behave. So how can we find for eigenvalues and eigenvectors? To find the eigenvalues and eigenvectors of a matrix A, we follow the steps. Step 1. Start with the eigenvalue equation. A times V minus lambda times V. And we will rearrange it to A minus lambda times I, quantity times V equals to 0, where I is the identity matrix of the same size as A and 0 is our zero vector. Step 2. Determinant condition. For there to be non-zero solutions for our eigenvectors, V, the matrix A minus lambda times the identity matrix must be singular. So it must have a determinant of 0. So determinant times A minus lambda times the identity matrix equals to 0. This equation is called the characteristic equation of A. Solving this polynomial equation gives the eigenvalues lambda sub 1, lambda sub 2, and lambda sub n. Step 3. Finding eigenvectors. For each eigenvalue x, solve the equation. To find the corresponding eigenvector, which is the v, this equation is a system of linear equations, and the solutions give the eigenvectors associated with lambda. Examples. So let's explore some examples to better understand the process of finding eigenvalues and eigenvectors. So for our step 1, we'll find the characteristic equation. So we start by setting up the determinant equation. So we calculate the square matrix minus lambda times the identity matrix. So our given is, our first row, we have 4, 1, 2, and 3, minus the lambda times the identity matrix, which is, so we will set 1 to the main diagonal, and we will set 0 to the remaining spot. So equals to, so if we simplify this one, so the answer is 4 minus lambda, and then this one is 1, and this one is 2, and the remaining is 3 minus lambda. Then we will find for the determinant. So we will just multiply 4 minus lambda to 3 minus lambda minus 2 times 1. So that is lambda squared minus 7 lambda plus 10 equals to 0. So our characteristic equation is lambda squared minus 7 lambda plus 10 equals to 0. So if we will find for eigenvalues, we will just factor this out to find for our roots. So we will use our factoring. So our factor here is lambda minus 5, and the other factor is lambda minus 2. So we will use zero property of equation. So we will transpose. So lambda sub 1 equals to 5 and lambda sub 2 equals to 2. So this 2 is our eigenvalues. So our eigenvalues is 5 and 2. So for our eigenvector, we will use our eigenvalues, which is 5 and 2. So we will set up the eigenvector equation, we'll start with the eigenvalue equation, which is A times V equals to lambda sub 1 times V. So we will subtract lambda sub 1 times V from both sides. So that is our square matrix minus lambda sub 1 times the identity matrix times V equals to 0. So where our identity matrix is 1, 0, 0, and 1. So now we will calculate. So let us substitute our lambda sub 1 to our equation. So our lambda sub 1 is 5. So we will replace it by 5. So so our equation is square matrix minus 5 times the identity matrix. So our given is 4, 1, 2, and 3. So minus our identity matrix, which is times by 5. So that is 5, 0, 0, and 5. And then we will simplify that one. So that is 4 minus 5. That is negative 1. 1 minus 0, that is 1. 2 minus 0, that is 2. And 3 minus 5, that is negative 2. So our next step is to set up the systems of equation. So based on our answer here, so let us multiply it by our v sub 1 and our v sub 2. So that is negative 1. So negative 1 times v sub 1 and 1 times v sub 2. That is our equation 1. And for our equation 2, that is 2 times v sub 1, and next is negative 2 times v sub 2. So this one. So that is our equation 2. So we will simplify that one. So our answer is negative v sub 1 plus v sub 2 equals to 0. So negative 1 times v sub 1, that is negative v sub 1. And then this one is positive v sub 2. That is our equation 1. And we will rearrange it to express v sub 2 in terms of v sub 1. So we will transpose this one. So the value of v sub 2 is v sub 1. And for our equation 2, so 2 times v sub 1, that is 2 v sub 1, minus 2 times v sub 2, that is 2 v sub 2, equals to 0. So we will substitute our equation 1 to our equation 2. So our 2v sub 1, so just copy, minus 2 times our v sub 2 is v sub 1. So we will substitute that 1. So 2v sub 1 minus 2v sub 1, that is 0. So 0 equals to 0. So this equation is always true, meaning it doesn't provide new information but confirms that v sub 2 equals to v sub 1. This tells us that v sub 1 and v sub 2 must be equal. So the eigenvector corresponding to lambda sub 1 equals to 5 can be written as, so we will just find for the numerical coefficient of this one. So this is 1, and our here is also 1. So where k is any non-zero scalar, the eigenvector is any multiple of the vector 1 and 1. So next, we will use our lambda sub 2 for our eigenvalue, or our second eigenvalue, which is 2. So we will set up the eigenvector equation. So we will substitute this one to 2. So our identity matrix will look this one. So we have 2, 0, 0, and 2. So minus, so 4 minus 2, that is 2. 1 minus 0, that is 1. 2 minus 0, that is 2. And 3 minus 2, that is 1. So we will multiply this one. So 2 times v sub 1 is 2 v sub 1. So 1 times v sub 2 is v sub 2 equals to 0. That is our equation 3. And next is 2 times v sub 1, so the same, plus 1 times v sub 2 is v sub 2 equals to 0. That is our equation 4. So, as you notice that both equations are the same. So, we will solve for the equations. So, 2v sub 1 plus v sub 2 equals to 0. So, we will express v sub 2 in terms of v sub 1. So, v sub 2 equals 2. So, we will transpose this 1. This is negative 2 v sub 1. So, the eigenvector corresponding to lambda sub 2 equals to 2 can be written as, so this one, our numerical coefficient here is 1, and this one is negative 2. So, our eigenvector is any multiple of the vector 1 and negative 2. And that's all for our eigenvector and eigenvalue.